Welcome back to our lesson about continuity, section 2.4. If you've not done so already, you should go back and watch the introductory video that you can link to using the QR code that you see on the screen now. We're going to skip over that content and look at some examples. For each of these functions, we're going to determine if there are any x values where the function is not continuous. And if there are, we're going to classify those discontinuities as either removable or non-removable. And then if they're non-removable, we'll see if we can learn a little bit more about the type of non-removable discontinuity. In the first example, f of x equals 1 over x, this is a very simple function. We in fact should already know what its graph looks like. So without using a graphing calculator, but using our basic knowledge of functions, we know that we have a function with a vertical asymptote that corresponds to the y-axis. Algebraically, when we look at the equation, we notice that x cannot be 0. So that means that the domain of this function is all x values except 0. Domain restrictions are important when you're analyzing continuity because they give you x values to examine as possible discontinuities. So in this case, f of 0 is undefined, and because f of 0 is undefined, f is discontinuous. At x equals 0. Now, in terms of the type of discontinuity, you can see from the graph that because we have a vertical asymptote, this is going to be a non-removable discontinuity. We can't change one single y value and make the function continuous. Therefore, this is a non-removable infinite discontinuity. When we look at example B, example 1, part B, we have a slightly more complicated function. This isn't one that we can draw the graph of easily without using our graphing calculator. But we can analyze the function in a similar way, thinking about its domain and then using that to help us determine whether or not we have any removable discontinuities. In this case, if we take the function and factor the denominator, it factors as the product of x plus 4 and x minus 6. From this we see that the domain of the function is all x values except negative 4 and positive 6. So negative 4 and positive 6 are possible discontinuities. In this case, both x equals negative 4 and x equals 6 are discontinuities, but one of them turns out to be removable and the other one does not. If we were to look at the limit as x approaches negative 4 of f of x, notice that in our algebraically simplified formula here, where we factored the denominator, that we could cancel the x plus 4 factors. So that limit is equal to the limit as x approaches negative 4 of 1 over just x minus 6. In this case, this limit can now be evaluated using direct substitution. The 1 over negative 4 minus 6, or negative 10. So the limit is negative 1/10. So since negative 4 is not in the domain, f of negative 4 is undefined. However, the limit as x approaches negative 4 exists and equals a real number. Therefore, we have a removable discontinuity at x equals negative 4. Rather, x equals negative 4. We have a removable discontinuity at x equals negative 4. It's removable because all we would need to do in order to make the function continuous at x equals negative 4 is to simply redefine the y value as negative 1/10. That would make the function continuous. However, when we examine the function at x equals 6, we see a different situation. At x equals 6, when we evaluate the limit, we still see so at x equals 6, when we evaluate the limit as x approaches 6, we can still use the simplified version of the expression, 1 over x minus 6. However, what you notice here is that we still have an expression of the form 1 over 0. This indicates that this is an infinite limit because we have a constant divided by a quantity that's getting closer and closer to 0. We'll talk more about infinite limits in a later lesson, but basically when you see this form that cannot be simplified further and the 0 cannot be eliminated, there's no way to cancel this x minus 6, that indicates that we have an infinite limit and therefore an infinite discontinuity. So we have a non-removable discontinuity at x equals 6. In fact, it is an infinite discontinuity. Let's move on to our next example. In this example, part C, example 1, part C, we have h of x, which is a piecewise function. I want you to notice that each piece of this piecewise function is continuous. Y equals x plus 1 is a linear function and therefore has no domain restrictions and no points where you might have a jump or a break. The same thing is true of y equals x squared plus 1. Its graph would be a parabola, no jumps, no breaks. So the only possible place where we might have a discontinuity is at the joint between the pieces. In this case, that's at x equals 0. So we need to investigate the limit as x approaches 0 from the left of h of x, and we need to investigate the limit as x approaches 0 from the right of h of x. The left-hand limit is going to be determined when x values are less than 0. So we're going to use the formula 0 plus 1, which of course is 1. For the right-hand limit, that's for x values bigger than 0, so we're going to use x squared plus 1. So using direct substitution, 0 squared plus 1, which is also 1. So we notice that the right and the left-hand limits are the same, so we can conclude that the limit as x approaches 0 of h of x equals 1. Now, the limit exists, but is the function continuous at x equals 0? Continuity says that the value of the limit must equal the value of the function. So we have to check and see, what does h of 0 equal? Well, in this case, we go back up here and we notice that we have equality in the first piece of the function. X is less than or equal to 0, so we use the equation x plus 1, in this case 0 plus 1, and see that h of 0 is 1. So now we conclude that because the limit as x approaches 0 and the value of the function at x equals 0 are the same, h is continuous at x equals 0. So h has no discontinuities. H is always continuous, or h is continuous everywhere. In our next example, example 1 part D, we're looking at the function g of x equals sine x. Now, there's not immediately any obvious x values that we need to examine. There's no division, so we can't have division by 0. There's not a piecewise function, so there's not a joint between the pieces that we need to check. We just have the sine function. If we think a moment about what the graph of our sine function looks like, it's a nice, smooth, continuous graph for all x values, which seems to imply that g of x has no discontinuities. Well, this is in fact going to be true, because the limit as x approaches c for any c of sine x is just going to equal sine of c. That the limit as x approaches c, no matter what that x value is, it's just going to be the value, the y value of the curve. So no matter which point I pick, c, the limit is always just going to be the height of the curve, sine of c. So since this is true, g of x equals sine x is continuous everywhere. No discontinuities. We have one final part for example 1, so example 1 part E. We have another piecewise function. F of x is x squared minus 4x plus 6 when x is less than 2, and is equal to negative x squared plus 4x plus 2 when x is greater than or equal to 2. So again, notice that each piece of this function, they're both quadratic. Quadratic functions are continuous on their domains, so the only place we need to check is x equals 2, the joint between the pieces. So we're going to look at the limit as x approaches 2 from the left of f of x, and we're going to look at the limit as x approaches 2 from the right of f of x. Now the left-hand limit, that's for x values that are less than 2, so I'm going to use the first equation. It's going to be 2 squared minus 4 times 2 plus 6. Well, 2 squared is 4, so we have 4 minus 4 times 2. 4 times 2 is 8. 4 minus 8 is negative 4 plus 6 is positive 2. The limit as x approaches 2 from the right, that would be x values that are bigger than 2, so we're going to use the second piece of the equation. Negative x squared in this case is going to be negative 2 squared, or negative 4, plus 4 times 2, which is 8, plus 2. Following order of operations, we've got to add from left to right, so negative 4 plus 8 is positive 4, plus 2 is 6. Well, notice that the limits are different. So, the limit as x approaches 2 of f of x does not exist. And because the limits are both exist but are different numbers, we know we have a non-removable jump discontinuity at x equals 2. One last example in this video. Example 2 is a type of problem that the AP exam likes to test a lot. Because this type of question allows them to see whether or not you actually understand the definition of continuity. So, we have a piecewise function. We notice that there's a constant a involved in both pieces of the piecewise function. So we're going to find the constant a such that the function is continuous on the entire real number line. We need to show a complete analysis of our conclusion. Now, what we notice first is that the two pieces, ax plus 1, well, that's linear, and we know that for any x value, a linear function is going to be continuous. The second piece is ax squared minus 1, a quadratic function, and again, for any x value, that piece will be continuous. So the only possible discontinuity is the joint between the pieces at, in this case, x equals 3. So we need to pick the value of a that makes the function continuous at x equals 3. First, I want you to notice that f of 3 is defined by the first piece, because that's where we have equality. This is x is less than or equal to 3, so f of 3 is a times 3 plus 1, or 3a plus 1. That's the value of the function in terms of a. Now we need to look at the limits. The limit as x approaches 3 from the left of f of x, well, because the left-hand limit is determined by ax plus 1, that's also going to be equal to 3a plus 1. The right-hand limit, x approaches 3 from the right of f of x, is going to be determined by the right-hand function. Now, its 3x squared minus 1, so that's going to be a times 3 squared minus 1, or 9a minus 1. Now, in order for the function to be continuous, we need all three of these quantities to equal one another. Well, two of them are already the same. The value of the function is 3a plus 1. The left-hand limit is 3a plus 1. So we only need to set the left-hand limit equal to the right-hand limit. So we need 3a plus 1 to equal 9a minus 1. We have a little equation to solve. If we combine like terms, subtract the 9a from both sides, we'll get negative 6a on the left, and we subtract 1 from both sides, we get negative 2 on the right. Dividing on both sides by negative 6, negative 2 divided by negative 6 is positive 1/3. So what this shows is that if a is positive 1/3, then we will have satisfied the definition of continuity. We can even write the equation of our function. F of x would be 1/3 x plus 1 when x is less than or equal to 3, and 1/3 x squared minus 1 when x is greater than 3. We could go back and retest continuity and show that the value of the function and the right and the left-hand limits are all the same at x equals 3 given a equals 1/3. This is the end of our video. We will pick up at this point in class on Tuesday.